Okay, so we are going to explore end behavior of functions, and we're going to start off with polynomial functions. So we already hopefully know from Algebra 2 that polynomial functions have four basic shapes in terms of their end behavior. Even degree, my arrows point in the same direction. So they either both point up when they have a positive leading coefficient, or they both point down when I have a negative leading coefficient. For an odd degree polynomial, my arrows point in opposite directions. And for odd degree, we're always going to look to our right arrow. So my right arrow points up here, so this is a positive leading coefficient. My right arrow points down here, so this would be a negative leading coefficient. So for each of the following, determine whether the polynomial is an even degree or an odd degree, and the sign of the leading coefficient. So my first one, my arrows point in the same direction. So that means it's going to be an even degree. And my right arrow points up, or in this case, they both point up, so it is a positive leading coefficient. My second one, my arrows point in opposite directions. So this would be an odd degree. My right arrow points up, so it is a positive leading coefficient. My last one, my arrows point in the same direction, so this would be an even degree polynomial. And my right arrow points down, so this would be a negative leading coefficient. So this is about the picture of the graph, the shape of the graph, the direction of the graph. Now we're going to go one step further, and we're going to start writing our end behavior. So before I jump right into writing your end behavior formally out in notation, we're going to talk about it in words. So describe the end behavior, which end behavior is really just predicting the outside part or the ends of the graph of the function shown below. So part A says as x increases without bound. So x is our domain. So this is my x-axis. So x goes to the left to positive infinity, to the right to positive infinity, or to the left to negative infinity. X's is domain left to right. So as x increases without bound, it is getting more and more positive, so it is going to the right. So on the right-hand side, what's happening to my function, my graph? My graph is going down and down and down and down and down and down. So the y values, more negative, more negative, more negative, more negative. My y values decrease without bound. And the reason it's without bound is because there's an arrow. So now the next one says as x, so again, I'm going left and right, decreases without bound. So I'm getting more and more negative for my x's, so I'm going to the left. So on the left, I'm going more and more and more and more negative, so the same thing. The y values decrease without bound. So this is your description in words. And in Algebra 2, we wrote our end behavior where we would say like, as x goes to infinity, f of x does this, and as x goes to negative infinity, f of x does this. This was the Algebra 2 notation. This is our words or description. Now we're going to talk about the more formal way that we're going to write end behavior from now on in limit notation. So end behavior with limit notation. So our left end behavior is as x goes to negative infinity, because on an xy axis, my x's on the left go to negative infinity. And that's where my x values decrease without bound. My right-hand limit, or my right-hand end behavior, is going to approach positive infinity. So on the right side, I'm going to positive infinity. And this is as my x values increase without bound. So let's take a look at an example. It says the function g is given by g of x equals negative 1.3 x cubed plus 4x squared minus 7. The function f is given by the graph below. Part A, determine the end behavior of g, so I got to go up here, as x increases without bound. So I'm going to start with my limit notation. So limit, which we represent with LIM, for g of x, because I always have to make sure I'm choosing the right function to look at and to write my notation with. X increases without bound, so that means x is going to the right. I'm going to positive infinity. So x approaches positive infinity. And I want to know what this equals. So now I have to remember my polynomial rules. This is a negative leading coefficient. This is an odd degree. So my graph goes like this. So on the right side, my arrow points down. So it goes to negative infinity. Part B, determine the end behavior of f. So f is this graph as x decreases without bound. So x decreasing without bound is going to the left. So I am approaching negative infinity. So limit LIM as x approaches negative infinity for f of x equals. So I'm going to go to my graph. Left is going up, 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 and up. So my y values keep getting higher and higher and higher and higher. So it is going to positive infinity. So that is the formal way that we are now going to write our end behavior. Whether it's from a graph where I'm showing you a picture, this one happens to be an exponential function, whether it's from an equation where I'm giving you an equation that you're either going to eventually type in a calculator or right now know our rules for polynomials and visualize what that picture looks like, we are always going to write limit notation for end behavior from this point forward.